Hi, welcome to Module 3, Video 3. In this video, we're going to talk about regular grammars. So just to remind you that a language is regular if you can construct a DFA or an NFA that accepts that language. There are two alternative methods to describe regular languages, and those are regular expressions and regular grammars. And this video is on regular grammars. All right, so let's review what a grammar is. A grammar is a quadruple or a four-tuple, VTSP. V is a finite set of objects called variables. Usually you use uppercase letters for these variables. T is a finite set of objects called terminal symbols, usually lowercase letters, usually the alphabet of the symbols of the alphabet. S is the start symbol. S is one of the variables. It's how you start to do your productions. P is a set of productions, and the production rules will specify how the grammar transforms from one string to another. Sets V and T are non-empty and disjoint. That means that if they're not empty, that means that you must have variables and you must have terminal symbols. Disjoint means that you cannot have any symbols that are both variables and terminal symbols. So terminal symbols are terminal symbols and variables are variables. So you do your productions from the left-hand side string to the right-hand side string. Some rules about productions, about grammars in general. The left-hand side, there must be a symbol. You must have a variable or a terminal on the left-hand side. If you are dealing with regular grammars, you will have a single variable on the left-hand side. The right-hand side, you can have the empty string. So the empty string is possible to have the empty string on the right-hand side. The empty string is made up of variables and terminal symbols, and you can have the empty string. On the left-hand side, you must have variables or terminal symbols, and in regular grammars, you can only have one single variable on the left-hand side and no terminal symbols. And on the right-hand side, you can have terminal symbols, variables, the empty string, but you still can only have one single variable. So we will go over that when you see the examples. It'll be much more clear. Linear grammars. In a linear grammar, all productions on the right-hand side have at most one variable. All right, so there are grammars in which you have more than one variable on the right-hand side. A linear grammar has only one variable on the right-hand side. If you want to describe a regular language with a grammar, it must be either a right linear grammar or a left linear grammar. So let's see what that means. A right linear grammar has at most one variable on the right-hand side. It also has only one variable on the left. So in a right linear grammar, you have only one variable on the left, and on the right-hand side, you have at most one variable. And when you have that one variable on the right-hand side will be all the way to the right. So all the terminal symbols in a right linear grammar will be on the left side of the variable. So any variables that are in a right linear grammar, the single variable on the right-hand side will be on the right side of all terminal symbols. In a left linear grammar, on the right-hand side, you will have your single variable, but your single variable will be the leftmost symbol. So the top is a right linear grammar where you can see the first production. We have a terminal symbol x followed by a variable b. And on the second example, a left linear grammar, we have on the right-hand side a terminal symbol b followed by, a variable b followed by a terminal symbol x. If you want to describe a regular language with a grammar, it would be either right linear or left linear. If you see this example down here, although this is a linear grammar, there's a right linear production and there's also a left linear production. So therefore, this grammar defined down here at the bottom, it does have all of the rules of a grammar, but it does not define a regular language. It is not a regular grammar. All right, so now we're going to look at this grammar. This grammar is a regular grammar. All of the productions are in the form of a single variable on the left-hand side and a single variable on the right-hand side, And if there is a variable on the right-hand side, meaning if there are any terminal symbols on the right-hand side, then the variable is all the way to the right, so this is a right linear grammar. So in order to construct a DFA that accepts this language, we're going to start by constructing an NFA, and then we're going to convert our NFA to a DFA. So this is more practice on, first constructing an NFA from a grammar, from a right linear grammar, and then taking that NFA and converting it to a DFA. So this is an exercise, and let's get started. So how do we construct our NFA? Well, we're going to start from our start symbol. So our start symbol, we can name our states whatever we want. So I'm going to use the variable names for the states, and any additional states I will have to give names later. So we start with our start symbol. We will consume an A and a B, and so when we consume the letter A, we go to another state, but I'm going to name that later. And you can see here, if we consume an A and a B, we will end up back in our state S. So that's the very first production. You can see up there A, B, and with the AB, we will end up in state S. All right, so let's go. What happens? What is the second production here, where we go this production right here? How do we show that in our NFA? Well, we start from our start symbol. We don't consume any, we start from our state S. We don't consume any symbols, so we would just take a lambda jump to the state A. So now we've done all of our, we've defined everything for our state S, so now we're going to move down to state A. State A, with a BA, we will go to state B. So you can see here, we consume a B and an A, and then we end up in state B. That's the only production we have there. So now from B, we have two productions. With an A, we will go back to state, with the symbol A, we'll go back to state A. And with two B's, we will end up in an accepting state. So take a look at this for a minute, and this should be able to understand that this is an NFA. It's an NFA. It has a lambda jump. It also does not have every transition defined for every symbol from every state. So once we have our NFA and we've constructed that, then we can take our NFA and use either the power set method or the table method. I'm going to use the table method to transform our NFA into a DFA. So take a look at it. We can review our productions. Our first production from state S with an A and a B, right? Oops. With an A and a B, we go back to S. So here, A, B, we go back to S. Then we have our next production from S with a lambda jump, because there's no symbols, there's no alphabet symbols there. We would just take a lambda jump to A. Then from A with a B and an A, that takes us to state B. And then from state B with an A, we would go back to state A. And with two B's, we will then end up in a final or accepting state. All right, so now let's turn our NFA into a DFA. So we're going to start by creating a table with all of our states. So in order to create the table with all of our states, I'm going to have to put names on all of the states. So I do have state S, and then the other states, I just added Q1, Q2, and Q3, and put an X for the final state, final or accepting state. And then we just define all of our transitions. I skipped the part of separating the lambda transitions and went ahead and went to the second table. All right, so let's just take a look. If you are in state A with the letter A, you are going to go to state Q1. If you are in state, I said A, but I meant S. If you're in S with a B, you have to take into account the one lambda transition we have here. So with a B, you're going to end up in Q. So again, take a look at this. From state S, with an A, you will go to Q1, and with a B, you'll go to Q2. If you're in Q1 with an A, it's not defined, but Q1 with a B is going to go to state S. If you are in state A with an A, it's not defined. With a B, it takes you to Q2. If you're in Q2 with an A, you go to state B, and with a B, it's not defined. If you're in B with an A, you go to state A, and with a B, you go to Q3. If you're in Q3 with a B with an A, it's not defined. We don't know because this is an NFA. And with a B, you go to state X, and X is an accepting state, but we do not have any of the transitions defined for state S. So take a look at that again. From state S with an A, you go to Q1. With a B, you go to Q2. From Q1 with an A, it's not defined. B, you go back to S. From A, state A with an A not defined. With a B, you go to Q2. Q2 with an A, you go to state B. And from Q2, it's not defined what you do with a B. From state B, with an A, you're going to go back to A. And with a B, you're going to go to Q3. And if you're in Q3, with a B, you're going to go to X. All right, so the next step is to draw all of these states for our DFA and add all of the transitions. So I'm going to, like I did before, I'm not going to use the same names, S, Q1, A, etc. I'm going to give them new names, P0, P1, P2. So you can see here that P0, that S is P0, so I put them in the order that they are on the table so that it's going to be in the same order. So let's start drawing our DFA. Just showed you that here I just renamed everywhere that it had, I don't know if I can go back. I don't like that I can't go back, but anyway, I just renamed. So when it said S, I just changed S to P0. Everywhere that it says, X, I changed that to P6. So everywhere, I just put the new names, and then I highlighted the new names here so we can start drawing our DFA. So I just left the old ones, but we're only going to really pay attention now to the highlighted ones that are in yellow. So we're going to start at P0. P0 with an A, we will go to P1. P0 with a B, we'll go to P2. So you can follow, I hope, what I'm doing here. Just take a look at the highlighted ones. Don't look at the old names, just look at the new names. All right. So now I'm in P1. From P1 with a I'm going to go to P7 or the trap state, and P1 with a B, I'm going to go back to P0. Then I'm skipping now because the next one defined on the table is P4, but I haven't drawn it yet on my DFA, so I'm going to skip down here to P2. So I've already done P0, I've done P1, and now I'm going to do P2 because P2 is already drawn. From P2 with an A, I'm going to go to P3, and with a B, I'm going to go to P7. So now I'm going to do P3. P3 with an A, I'm going to go to P4, and with a B, I'm going to go to P5. And now I'll do P5. Oh, I don't know if I'm doing P4 or P5. Now I'm going to do P4. So I'm going to go back here to P4. With an A, I go to the trap. And with a B, I go back to P2. And now I'll do P5. P5 with an A, I go to the trap. And with a B, I'm going to go to P6. And P6 is an accepting state because P6 was state X, if you remember here. All right, then if I'm in P6, I'm going to go to P7 with an A or a B. And then if I'm in P7, of course, I'm going to stay in P7 with an A or a B. So I've now converted this NFA into a DFA. And of course, since this is a video, you can go back and rewind, or you can actually try and do it yourself for practice. Now we're going to try to make a regular grammar from a defined language. So the first step in doing that is to understand the language, try to come up with some strings that are in that language, then we'll create an acceptor like an NFA for that language, and then we'll convert our NFA into a regular grammar. All right, so let's get started. First thing is, let's look at this language. This language is any number of A's followed by a number of A's followed by a number of B's, but the number of A's and the number of B's, when you add them together, must be odd. So the single letter A is fine. The single letter B is fine. 1A and 2 B's is fine. 2 A's and 1 B. So I've come up with some strings that are part of this language. A couple that I did not include would be 3 B's, that's okay, or 5 B's, an odd number of B's, odd number of just A's, that's fine. I didn't, we could add here just odd numbers of A's, like no, anyway, just a simple odd number of A's, odd number of B's, or a combination of A's and B's that are odd, as long as we begin with an A. So you can't have any, if you get a B, you cannot have any A's after your B's. All right, so let's get started. So we're going to use symbols that similar to our grammar to help to translate to a grammar. All right, so we're going to start. A single letter A is in the language. A single letter A followed by 2 B's is in the language. So when I start to create a DFA or an NFA for a language, I usually come up with a bunch of strings, and then I start by building some states with some and get to some accepting states, and this will be an NFA, so we don't have to define everything. We just have to make sure that at some point any of these strings will end up in an accepting state. All right, so now what about a single B? Yes, we have a single B will lead to an accepting state. So what about AAB? All right, here, even though this AAB leads to a not accepting state, this AAB leads to an accepting state. So that's why this is, sometimes it's easier to create the NFA. All right, what about A, B, 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 or even B, 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 right? So we have a single B, and we have A's followed by B's, but now we need to deal with multiple B's. So here, if we have 2 B's, it's not accepting, but if we have 3 B's, that is accepting. So that works. B, 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 5 B's, 7 B's, so we took care of that. What about 3 A's, A, yes, odd number of A's is also here, 3 A's, 5 A's, we took care of that. What about 4 A's and a B? A, B. Yes, so I think that this is a good NFA for this language. So this is a regular language. So now the next step is to translate our NFA into a grammar. All right, so here we are. So we just start from the beginning and we create our productions. So from your start with an A, if you consume an A, you're going to end up in state A. From state S with an A, you get to state A. Also with a B, you get to state B. So from S, we have 2 transitions. We therefore have 2 productions. Now let's do from A. So A with an A, you go back to S. A with a B, you go to X. And then A, you can also stop at A because A is an accepting state. So you could also just stop there and not consume any strings and end there as one of the accepting strings of the language. All right, now we start from X. X with an A is not defined, but if you are in state X and you get a B, you can go to state A. If you're in state X with a B, you go to state A. And this is an error because you're not going to go, that's the same, so this should actually be a B. So from state X with a B, you can go to state A, or state X with a B, you can go to state B. So we have, again, it's an NFA. We have two different transitions from state X with the symbol B. From state B with a B, you can go back to X. And from state B, you can also stop there because it's accepting. So these two are accepting, and therefore they will, that's why you have the empty string there. You're not going to consume anything. You're going to end there, and that would be, accepting. All right, so here is the grammar written the way that we've been doing it, and this is correct here. It's just messed up here on that part. So this is a grammar for this language. This is an NFA for this language. If you want to practice, you can try to convert that NFA to a DFA, and this is a regular language.